3.3.0, reading schematic diagrams. Read simple schematic diagrams. Identify the symbol for a resistor and determine its value based on color codes. Distinguish between series and parallel circuits. Identify the instruments used to measure circuit values. A schematic diagram illustrates a system using symbols in place of realistic pictures. In this section, you'll learn how to identify the symbols used on schematic diagrams showing circuits. You'll also learn how to recognize different types of circuits and the test instruments used to measure circuit values. So a schematic diagram is a type of drawing in which the symbols are used to represent the components in a system, also referred to simply as a schematic. It says, think back to the simple circuit shown earlier in this module. Now look at figure 17. This figure shows the same pictorial illustration next to a schematic or line diagram of the circuit. Note the same system components are shown in both drawings. So here's a battery. You go through the negative wire, through the switch, through the other wire to the light socket. It goes through the filament of the light bulb and comes back on the red wire, returning to the battery. And here's the same pictorial representation of that circuit. This is the battery, negative, positive. We're coming from the negative to the switch, through the wires, to the filament of the light bulb, and back to the positive of the battery. When you look at the schematic drawing, you'll see that there are standard graphic symbols for common electrical and electronic components. That makes it easier to identify what you're looking at. Refer to figure 18 to see some of the standard schematic symbols. So here's figure 18. This is an AC power source. There's a sine wave. This is a battery. There's a circuit breaker, control relay. These are contacts. These are normally closed and these are normally open. When they talk about contacts being in the normal position, that position is de-energized. It's off the shelf, out of the box, in your hand. Are those contacts closed or open? If you ring through them and you have continuity, they're closed. If you ring through them and you have an open circuit, they're open. This is usually the schematic for a fuse. Sometimes people draw it like this, a barrel fuse. This represents ground. This often is used as a chassis ground. Here's a lamp. Here's a motor. Here's a DC motor. A fixed resistor, a variable resistor. You can see the arrow makes it variable. A switch. These wires are connected. They're electrically joined with a wire nut. These wires are just crossing each other. They're not connected. 3.1.0, resistors. A resistor is manufactured to offer a certain limited amount of resistance to a circuit. It's a fixed number. Function of a resistor is to offer a specific resistance to current flow. The two most common types of electronic resistors are the wire wound and the carbon composition. So here's wire wound. You can see the wire that's wound around the outside of a porcelain tube. And these are the carbon compound or composite. They're showing you the inside of it. You have nickel resistance wire. There are ceramic tubes, and the whole thing is coated in a porcelain coating. And they make them very specific to be a certain number of ohms. It can be anywhere from 0.1 ohms up to, a million ohms. Connecting wires. The color banding. We'll learn about the color banding. And here's the schematic for a variable resistor. They're saying this one's a rheostat because it's 2 leads, and this one is a potentiometer. It actually has 3 leads. You can change the voltage to the output by sliding this. That's why it's called potentiometer, potential voltage. It's adjusting the output voltage. Resistor color codes. So you have 3, 4, or 5 bands. If you only have 3 bands, the first 2 are the digits, the third is the multiplier, and the fourth band is none. It means it has a tolerance of 20%. That resistor has a 20% tolerance. As you get into higher quality resistors, they'll have a 10% or a 5% or a 1% tolerance, meaning they're going to be very specific as to if they said it was 1,000 ohms and it's a 1% plus or minus, that means it's 990 ohms to 1,010 ohms, plus or minus 1%. That's the tolerance. So here's our color coding: black, brown, red, orange, yellow, green, blue, violet, gray. And then you have gray and white. And you have gold and silver, and tolerance of gold or silver. Gold is 0.1, silver is 0.01, and then the tolerance is 5% for gold, 10% for silver, and 20% for no band at all. And you can remember this if you write down the mnemonic. You say, better be ready, or your great big, this is purple, plans go wrong. Get success now. Gold, silver, none. Get success now. So these represent digits and multipliers. So brown is 1 or 10 to the first power, which is 10. Red represents the number 2 or 10 to the second power, which is 100. Orange is the number 3 or 10 to the third power, which is 1,000. Yellow is the number 4 or 10 to the fourth power. Green is 5 or 10 to the fifth power. Blue is 6 or 10 to the sixth power. Purple or violet is 7 or 10 to the seventh power. Gray is 8. White is 9. So here they have these 4 bands. All right, well, the fourth band, if it has 4 or 5 bands, the fourth or fifth band is the tolerance. So this one has gold and it's plus or minus 5%. These 3 bands represent the 2 digits. Brown is 1, black is 0, that's 10, times red is 10 to the third power, which is 100. I'm sorry, 10 to the second power, excuse me, which is 100. So this is 10 times 100, or 1,000. So the value of this resistor is 1,000 ohms, plus or minus 5%. That's how you use the color coding. 3.2.0, series versus parallel circuits. You'll often hear the terms series circuit and parallel circuit. These terms refer to the way the loads are connected in a circuit. 3.2.1, working with series circuits. A series circuit provides only one path for current to flow, and it is a voltage divider. The total resistance of a series circuit is equal to the sum of the individual resistances in that circuit. 12-volt series circuit shown in figure 23 has 2 30-ohm resistors or loads. The total resistance can be calculated as follows. Add the 30 plus the 30 to get a total of 60 ohms. Since you now know both the resistance and the applied voltage, you can use the following Ohm's law formula to determine the current in the circuit. So 12 volts divided by 60 ohms equals 0.2 amps. The voltage drop is the voltage measured across any one of the loads. It depends on the resistance of that load and can be found using the following form of Ohm's law. The voltage drop equals the current running through the resistor times the resistance. So 0.2 amps times 30 ohms equals 6 volts. So if we had a voltmeter and we went across this R1, it would say 6 volts. And if we went across R2, it would say 6 volts. And the two of them together equal 12 volts. The voltage drops in a series circuit are additive. This proves that a series circuit is a voltage divider as it splits the applied voltage of 12 volts into 2 6-volt loads across each resistor. This is highlighted. The sum of all the voltage drops in a series circuit is equal to the total voltage applied to the circuit. So E equals 6 volts plus 6 volts equals 12 volts. So here they have four 30 ohm resistors in parallel, 30, 60, 90, 120. We have 120 total ohms of resistance. 12 volts divided by 120 ohms is 0.1 amps. The current flow would drop to 0.1 amps and be the same across all the loads. It can be calculated as follows. 12 volts divided by 120 ohms equals 0.1 amps. Voltage drop would be 3 volts across each load. It is calculated as 0.1 times 30 ohms equals 3 volts. The sum of all the voltage drops in the circuit is equal to the total voltage applied to the circuit. In this case, the voltage is divided by the four resistors, 3, 6, 9, 12. Note, circuits containing loads in series are uncommon. An important trait of the series circuit is that if the circuit is open at any one point, no current will flow. For example, old-style holiday lights were connected in series. If one of the lights burned out, the whole string went out. 3.2.2 Working with parallel circuits. In a parallel circuit, each load is connected directly to the voltage source. Therefore, the voltage drop across or through each of the loads is the same. Here's 30 ohms, 30 ohms, 30 ohms. And there's a 12-volt source. Well, there's 12 volts across R1, there's 12 volts across R2, and there's 12 volts across R3. In a parallel circuit, the total resistance is less than the smallest of the individual resistances. Okay. All right, I don't see any highlights. Two resistors in parallel, 10 and 15. Let's see, where do I have some highlights? Suppose you have three 30 ohm resistors in parallel. What is the total resistance? They're in parallel. Well, it's 30 ohms divided by the number of resistors in parallel, 3. If all three of them are the same value, you can take the resistance of one resistor and divide it by the total number of resistors, as long as they're all equal. If they're all 30 ohm, then 30 ohms divided by 3 is 10 ohms. The total resistance in this circuit is 10 ohms. Working with series parallel circuits, well, sometimes we have a combination. We have to figure out what parts are in series and what parts are parallel. If you you trace the current with your finger and you go through a resistor without going anywhere else, that resistor is in series with the load. Same with R5. You can trace the current through it and it goes right back to the battery. So R5 is in series with everything else in the circuit. R1 is in series with everything else in the circuit. Our resistors 2, 3, and 4, however, are in parallel because here's a node and here's a node. So that's one path for current to go. Here's a node and here's a node. That's a second parallel path. And even though there's not a node showing, the voltage comes or the current comes from the battery or from the source up to here and continues on. So we have a voltage drop across R4 as well. Identifying circuits. The terms series circuit, parallel circuit, and series parallel circuit refer to the way the loads are connected. It's rare to find loads connected in series or in a series parallel arrangement. The simple circuit shown in Figure 29 illustrates the point. At first glance, you might think this is a series parallel circuit. On closer examination, you can see that there are only two loads, the relay and the contactor. This is a parallel circuit. So here's the fan relay and here's the compressor contactor. So there are two loads, one on this ladder, this rung, and one on this rung. Electrical meters. Electricians often use test meters to measure voltage, current, and resistance. The most common test meter is the voltomillimeter, millimeter. It is also called a multimeter. Figure 30 shows digital and analog multimeters. So this one is digital, gives you a readout. This one's analog because it has a needle that floats over this face and points generally to how many volts, how many amps. You use multimeters to measure AC and DC voltage, DC current, and resistance. You can also use them to measure AC current in the milliamp range. Warning test equipment may only be used by qualified individuals wearing appropriate personal protective equipment. Consult your company's safety policy for applicable rules. 3.3.1 Measuring current. For larger current values, you can use a clamp-on ammeter. And here's an example of a clamp-on ammeter. Always wear all the required personal protective equipment when using a meter. Also follow the manufacturer's instructions and your company's safety procedures. Keep the following precautions in mind when using a clamp-on ammeter. If the ammeter jaws are dirty or misaligned, the meter will not read correctly. Meters are precision instruments must be handled carefully to avoid damage. An analog meter can be damaged when the current far exceeds the selected scale. When using an analog meter, always start at the highest range on the meter and work down. That is highlighted. When using an analog meter, always start at the highest range on the meter and then work down. Do not clamp the meter jaws around two different conductors at the same time. This could lead to an inaccurate reading. So here's an inline ammeters must be connected in series with the circuit. I don't like using inline ammeters because you have to turn the circuit off and tag it out and then hook your leads up to the circuit. Then go take the lockout tag out off and restart the system and take your reading. Then you have to use lockout tag out, turn off the power, and go remove your meter from the circuit. So it's a lot of wasted steps. Measuring voltage. If a circuit function is not operating, a voltmeter can be used to determine whether the correct voltage is available. This is highlighted. It says a voltmeter must be connected in parallel with the component or circuit to be tested. Voltage must be checked with power applied. Voltage must be checked with power applied and the test leads connected in parallel with the component in question. Okay. This is giving us three 30 ohm resistors in parallel. So if we did the Ohm's law, we'd know that 30 divided by 3 equals 10 ohms. We have a total of 10 ohms. And we have 12 volts. The reason we have 12 volts is because it's a 12-volt source, and each one of these parallel resistors is across the source. Measuring resistance. An ohm meter contains an internal battery that acts as a voltage source. This is highlighted. Therefore, you must always make resistance measurements with the system powered off. Here's another highlight. It says usually you use an ohm meter to check for circuit continuity. Continuity means that the circuit is continuous with no breaks in the wire. So here's a system that they're checking with their continuity tester to see if the low pressure switch and the high pressure switch are closed. They should get a 0 reading when it comes to ohms. Let's see here. Testing for continuity. Okay, well, this says strip the insulation off a wire to be tested at both ends of the conduit run. Use an alligator clip to connect the wire to an equipment grounding conductor, either metal conduit as shown here, or a bare grounding conductor. So we're shorting this white wire. The green and the black are still insulated. At the other end, we're going to take a voltage reading or continuity reading from the pipe to the white wire. Then touch the probe to the end of the wire under test. If the tester audible alarm sounds, then or the indicator light comes on, there is continuity. Okay. Section 3.0.0 review. A resistor with a gold band in the fourth position has a tolerance of 5%. Gold band is a tolerance of 5%. The total resistance in a 120 volt series circuit with three 10 ohm resistors is 30 ohms. It's a series circuit, so we just add them together. Which of the following is true regarding the use of a clamp-on ammeter? D, misaligned meter jaws can, no, I'm sorry, C, no. Place the jaws around an even number, no. Place the jaws around, okay, I'm sorry, A. Place the jaws around a single conductor at a time. I misread that when I read it the first time. The answer is A. Which of the following is true regarding the use of a clamp-on ammeter? A. Place the jaws around a single conductor at a time. Well, this concludes our 26103 video lecture. I hope you got something out of it. If you did, please like and subscribe, and I'll see you on the next video. Thank you. Hey, this is Brian Young. If you liked my video, please give it a thumbs up and consider subscribing. I'll see you on the next video.